Hello friends, good afternoon and welcome to the EduSat Network. Today's lecture is part of our ongoing series on chemical thermodynamics, and friends, in specific today we talk about thermochemistry, and this shall be the third part of the same topic, wherein we have already covered the first and second ones, and you have the luxury to watch the first two on YouTube in case you have missed out on those. So friends, to take this topic further, we have with us in our studio subject expert Dr. Amit, Assistant Professor, Department of Chemistry, Dayal Singh College, University of Delhi, and sir has been associated with us on previous occasions as well, and I am extremely grateful to sir for having come here and joined us today also. So thank you so much, sir, for coming, and I request you to begin our today's lecture.
Thank you very much. Dear friends, as you all know, in the subject matter of thermochemistry, we are already having two lectures previously, where we started with the formulation of enthalpy of a reaction and conceptualizing it in terms of difference of molar enthalpy of products and that of the reactants. Following which, we also came to understand that molar enthalpy of substance is a quantity which cannot be determined absolutely. So therefore, that was posing a problem towards the calculation of enthalpy change of a reaction. In order to solve for this problem, we had introduced the concept of enthalpy of formation of compounds, and using which and further conceptualizing the fact that molar enthalpy of elements in their most stable state of aggregation under standard conditions being considered as 0. With these two considerations, we formulated once again the enthalpy of reaction in terms of enthalpy of formation. However, it was also leading to certain problems thereafter, because enthalpy of formation for formation reaction of majority of the compounds cannot be determined accurately. So therefore, we had to solve for this problem. So therefore, we introduced enthalpy of combustion also, which was also by virtue of relationship of enthalpy of combustion with the help of Hess law towards the calculation of enthalpy of formation, which can be used for the calculation of enthalpy of reaction. So till this point of time, we had covered all this. So we start with where we had left in the previous lecture. So let us have a look at that. We need to again consider that when benzene undergoes combustion to produce carbon dioxide and liquid water, how much heat is released per mole of benzene being combusted. So this we would like to see by virtue of having a numerical problem. So let us consider the combustion reaction of benzene. In the combustion of reaction of benzene, you can easily see that if we see that combustion reaction, then it has 2 moles of benzene, which combines with 15 moles of oxygen, and then to produce 12 moles of carbon dioxide, and 6 moles of water also gets produced. So as I told you, for any reaction, when we write a thermochemical equation, then it involves the stoichiometric coefficient, which appear in the balanced thermochemical equation, and balancing can be achieved in different manner. So therefore, here in this combustion reaction of benzene, we have 2 moles of benzene being combusted, but we always have if we want to define the enthalpy of combustion, it is the enthalpy change accompanying the combustion of 1 mole of the compound into the formation of carbon dioxide and water. So therefore, here we can see here 2 moles of benzene is being used. So we would like to address this also. Just have a look at it, what way we go. As you all know that this is the combustion reaction, and enthalpy change for this reaction, we can write it as sum of standard enthalpies of formation of products less the sum of standard enthalpies of formation of reactants. Where in this case, you can see we have 2 chemical species in the product side. There is carbon dioxide and also there is water. So 12 is the stoichiometric coefficient, so we multiply 12 for carbon dioxide, we multiply 12 with molar and standard enthalpy of formation of carbon dioxide, and add to this is the 6 times standard molar enthalpy of formation of water, and from this sum we subtract 2 times the standard enthalpy of formation of benzene. Please note that there is no term corresponding to oxygen here, because oxygen is molecular dioxygen is the elemental oxygen which is stable, which is the most stable state of aggregation under standard conditions. So, therefore, this a term corresponding to enthalpy of formation of oxygen does not figure in this equation. As a result, we have in this enthalpy, standard enthalpy of reaction, we have only 3 terms. The one relates to the sum of standard enthalpies of formation of products, from which we subtract 2 times the standard enthalpy of formation of benzene. So, now if we tabulate the data, all these values are in kilojoule per mole. So, therefore, 12 into minus 393.5 kilojoule per mole, which is the standard enthalpy of formation of carbon dioxide, plus 6 times the standard enthalpy of formation of water, which is minus 285.8 kilojoule per mole. And from this sum, we need to subtract 2 times the standard enthalpy of formation of benzene, which is 49.04 kilojoule per mole. So, finally, we get total enthalpy as minus 2635 kilojoule. But as you all know, here we had in this reaction, which we had written in the balance as a balanced chemical reaction, we had 2 as the stoichiometric coefficient for benzene. So, if we go by the definition of the combustion reaction, it is the 1 mole of the combustible compound when undergo combustion, it is the enthalpy change in that reaction represent the enthalpy of combustion. So, therefore, all we need to do is whatever the resultant value we achieve, we need to divide it by 2, that is the stoichiometric coefficient of benzene to lead it to 1. So, therefore, what we get is minus 3267 kilojoule per mole as the standard enthalpy of combustion of benzene. So, all we have done here is we have used the data on enthalpy of formation of for these reactant and product species, and we have calculated the amount of heat that will be produced for every 1 mole of combustion of benzene. That is how much heat will be released when 1 mole of benzene undergoes combustion, and we had the one data that standard enthalpy of formation of benzene is 49.04 kilojoule per mole, and other data of standard enthalpy of formation of carbon dioxide and water also we had with us. Now, having said this, let us now switch on our attention once again to the enthalpy change for a reaction. You see, the enthalpy of a reaction basically is the difference between the sum of molar enthalpies of products and the molar enthalpies of the reactants. If you see, when a reaction occurs in a system, then heat corresponding to the difference between the enthalpies of products and reactants is either released or absorbed by the system. So, therefore, we can say that the heat which is being transferred to or fro from the system to the surrounding basically is equal to the difference between the enthalpies of products and reactants. As a result, we can say that neither the heat has been produced nor has been consumed, but basically the one form of energy is just been converted into other form of energy. That is to say, suppose if a reaction is endothermic in nature, endothermic means the enthalpy, molar enthalpies of reactants would be at a lower value and some of molar enthalpies of products would be at a higher value. So, whenever a reaction in this reaction, the reactant to transform from reactant to the product side, then what happens is that heat corresponding to the enthalpy change of the reaction is being absorbed, gets absorbed by the reaction system, which comes from the surrounding. So, basically heat neither has been destroyed, energy here neither has been destroyed nor has been created, but actually from the surrounding the heat has entered the system and that is being stored within the chemical system as the in the form of potential energy in the product molecules. So, therefore, all we can say is here the energy does not get created or nor get absorbed. For example, if we talk about exothermic reaction, we say that heat corresponding to the difference between molar enthalpy of reactants and products is released to the surrounding. It is not that heat which gets produced, but basically it gets released because of the change in enthalpies of the chemical species in the within the reaction system from the reactant side to the product side. And basically this is the reason we can say that the thermochemical observations, that is the reactions, all these are in accordance with the first law of thermodynamics, which says neither the energy can be created or destroyed, but it only transforms from one form to the other. So, we can say that if reactants are at higher enthalpy, higher potential energy corresponding to the in comparison to the products. So, heat corresponding to the difference between potential energy will be released to the surrounding. So, therefore, the energy which was stored in the reactants as their potential energy has been transferred to the surrounding by virtue of a decrease in the potential energy of the reaction system, whereas converse the opposite thing occurs in an endothermic process. So, we can easily say that energy can neither be created here in chemical reactions nor can be produced. So, therefore, we can only say that these chemical reactions, thermochemical reactions, are in accordance with the first law of thermodynamics. Right. Having said this, now we need to switch on our attention to the Hess law. There is a very important law, as we have already mentioned, that enthalpies of formation data we utilize for the calculation of standard enthalpies of a reaction, standard enthalpy change of a reaction. For those reactions in which standard enthalpy of formation of the compounds which do take part in the chemical reaction, in the desired chemical reaction is not available, then we make use of standard enthalpies of combustion for those compounds, and from which we make use of those combustion reactions and enthalpies of combustions for such compounds, and we do determine the enthalpies, standard molar enthalpies for those chemical species, which we tabulate in the enthalpies of standard enthalpy change of a chemical react of the desired chemical reaction. So, now the question arises, because combustion reactions were also having some limitations associated with them, that they were applicable only for the organic chemical systems, that is organic chemicals for which the organic chemicals are made up of only carbon, hydrogen and oxygen. And if there are some heteroatoms which are present in the organic compounds, for them there was an issue of the definite proportions in consideration, as a result of which we cannot determine the exact value of, we cannot rationalize the standard molar enthalpies of the various compounds from the enthalpies of their combustion. So, now question arises what to do, because for a desired chemical reaction it is important that we determine its standard enthalpy change. So, here comes the Hess law into consideration. What is Hess law? If we need to understand it, we need to once again switch on our attention to the reaction system. In a reaction system, when a reaction occurs, some definite set of reactants do transform from definite set of products. So, therefore, what happens as a result of a reaction, there occurs a definite change in state of the system from initial state to the final state. As a result of this, there also occurs a definite change in enthalpy of the system. So, therefore, because enthalpy is a state function, because enthalpy change is a definite value in the reaction system, it means that if we write a desired chemical reaction as just in one step, or we write it as a combination of several other reactions, then we add them up. In that situation, either the enthalpy of the enthalpy change for the reaction will be the same. All we want to say is that no matter if we write a certain sequence of reactions, add them up and finally get a overall reaction, or we write the overall reaction straight away, the enthalpy change by following either sequence of reactions, the enthalpy change for the overall reaction will be the same, because there occurs a definite change in state when a reaction occurs, that is transformation of the system from a definite initial state to the definite final state. So, that transformation can occur following one sequence of steps or some other sequence of steps. Finally, it will lead to the same products. So, that is what we make use of as an observation, and we formalize a law that is called Hess law. And according to Hess law, that if a reaction be expressed as a series of steps, then the enthalpy change for the reaction of the overall reaction is the sum of the enthalpies of the reactions for each step. This we can see very easily, that if suppose there is a reaction in which we have a transformation of A plus 2B which lead to 2D, then we can see that it could also be possible that these two reactants do combine to give a intermediate product C, which when do transform to final product 2D. So, basically if we say delta H1, that is the reaction between A plus 2B which lead to C, and there is a reaction when A plus 2B do lead to 2D. So, basically we have two reactions in which A plus B do form C, and there is another reaction also in which A plus B do form D. So, therefore, we can get the enthalpy change for the reaction between C and D if we cannot determine it experimentally by just manipulating, by just adding the two reaction, that is adding the reaction 1, that is delta H1, which is the A which when combines with B and form D, and we can add to this the reverse of the reaction 2, or that is A plus B when combines to give C. Well, having said this, so therefore Hess law of heat summation is also known. Thus, for a chemical equation that can be written as the sum of two or more steps, the enthalpy change for the overall equation is the sum of the enthalpy change for the individual step. What consequence we draw from Hess law? It is important to note that Hess law is a result of or a consequence again of the first law of thermodynamics. So, basically according to the Hess law, we can write a reaction in a single step or as a combination of several reactions. When the overall reaction is been the same, the enthalpy change for that overall reaction will always be the same, no matter which sequence we follow to write the overall reaction. So, this is what we should understand from the Hess law, but the consequence we should understand, which we should draw from Hess law, is that according to the Hess law, it means that all thermochemical equations, we should treat them as algebraic equations. Like those of algebraic equations, we should be able to manipulate these thermochemical equations also. That is, we should treat them as algebraic equations, and since we can add one algebraic equation to that of the other to get another algebraic equation, then here also we can add several thermochemical reactions or subtract from certain thermochemical reactions some other chemical reactions to get to the overall thermochemical reaction. And when we do so, we need to manipulate we need also to add and subtract the corresponding enthalpies change of those reactions which we had added and subtracted to get to the final overall reaction. The enthalpy change for the overall reaction will be that sum and difference of those enthalpy change of those reactions which we had added to or subtracted from during the manipulation of the thermochemical reaction. Right. Having said this, we can have an understanding of this Hess law with the help of a numerical exercise also. So, let us see that suppose for example, we have a data set as you can see here, when sulfur in the solid state, the rhombic sulfur do combine with oxygen and form sulfur dioxide in the gaseous state. That is this is the enthalpy of, this is the formation reaction for sulfur dioxide. That is 1 mole of sulfur dioxide gets produced from its elements in their most stable state of aggregation, and the standard enthalpy for this standard enthalpy change for this reaction is minus 297 kilojoule per mole. Whereas if we have sulfur trioxide with us, and when it decomposed to give sulfur dioxide and molecular oxygen, then the standard enthalpy for this reaction is 198 kilojoule. Now, the question arises per mole each values. So, now the question arises, could you use this data to obtain the enthalpy change for this reaction, which is just nothing but the combustion reaction of sulfur, that is the sulfur which when combined with oxygen to produce sulfur trioxide. Now, can we use the data set and these two thermochemical equations written over here to determine the enthalpy change of this third reaction, that is the combustion reaction for sulfur? Now, the answer lies in the fact that yes, we can do so. All we need to do is we need to multiply the first equation by a numeric value 2, and we need to write the, now you can see the first reaction we have multiplied by 2. So, the stoichiometric coefficient in the first reaction of all the chemical species which do take part in the chemical reaction is 2. For example, sulfur in solid state has 2 as the stoichiometric coefficient, oxygen also has 2 as stoichiometric coefficient, sulfur dioxide also has 2 in the as the stoichiometric coefficient. So, now for this reaction which is now written as 2 times the first reaction for which we had the data, since we have multiplied by a numeric value 2 to the first reaction, and we get this another equation that is indifferently balanced. So, now we need to multiply also by a factor of 2 with the enthalpy of the first reaction to get to the enthalpy change for this reaction. That is, delta H standard for this reaction would then be equal to minus 297 kilojoule into 2 per mole. So, now we can write the second reaction which we had, that is the decomposition of sulfur trioxide, we can write it as reverse of this reaction. So, you can easily see the second reaction was having 198 kilojoule per mole as its value. So, since we have reversed the reaction, so we need to reverse the sign of delta H also. So, the sign reversal can be achieved by multiplying the delta H of this reaction by a numeric value, that is minus 1. So, that is the changes we bring about in these two, the initial two chemical reaction to get these final reactions. So, now we can sum up these two chemical reactions and let us see what we get. What we get is, when we do so, then the sulfur dioxide from left hand side and right hand side of the two equation, they do cancel. When we sum up the two reactions, what we get is 2 sulfur in solid state plus 2 oxygen in gaseous state, which leads to 2 moles of sulfur trioxide also, and we can manipulate, that is, we can just add these resultant equations, their enthalpies we can add to get the enthalpy change for this final overall reaction, that is minus 792 kilojoule. So, therefore, similarly we can determine the enthalpy change for combustion reaction of methane just by giving the values of various other enthalpy chains, that is, for example, methane and oxygen, which when do the methane, which when do decompose to form carbon to graphite to hydrogen. This is not the reaction actually, this is the formation reaction, which is basically the carbon in the solid state in the graphite form, which when combine with hydrogen and do form methane. This is the reverse of formation reaction, which is known as decomposition here. And we also have a reaction, that is a combustion reaction, when methane do combines with oxygen and do form carbon dioxide and water. So, basically we have formation reaction of carbon dioxide, we have the data set on this reaction, and we also have the data set on formation reaction of water. So, when we add these two and subtract from this is this decomposition reaction, so it is clearly the what we get as the overall reaction is the formation reaction. So, in this way, the combustion reaction here which is shown in the violet. So, in this way we can make use of Hess law just to manipulate the thermochemical equations just to get the overall chemical reaction. And for the overall chemical reactions, if we want to determine enthalpy, standard enthalpy change, we also need to manipulate the we also need to carry out calculations and manipulate the values of standard molar enthalpies of the respective chemical reactions which have been added and subtracted, so as to get the enthalpy change for the overall reaction. So, this is what we infer from Hess law. There is another application for the Hess law, that lies in the determination of lattice energy. Basically, what is the lattice energy? Lattice energy is the energy required, which is required to break down these lattice 1 mole of a compound in solid state into the gaseous atoms. So, basically for this, since we cannot determine the enthalpy change for this decomposition of lattice into gaseous atoms. So therefore, gaseous ions, sorry. So therefore, all we need to do is we can make use of Hess law to determine lattice energy for any given solid. For example, we take sodium chloride. You see, we can take the formation reaction of sodium chloride as combination of sodium ions, as combination of sodium metal with chlorine, which when do react do form sodium chloride. The balanced thermochemical equation is written over here. If we want to decide if the compound will be stable or not, as an ionic salt, the answer comes from the lattice energy. So lattice energy, how we would determine is by use of a Born-Haber cycle. Now it is time for us to look at what is Born-Haber cycle and how we can make use of it to determine lattice energy. You see, when we say formation reaction of sodium chloride, we need to consider sodium as solid substance which combines with chlorine gas and forms an sodium chloride solid. This is the enthalpy of formation of sodium chloride. So if we have data set on enthalpy of formation, then we can achieve the same formation reaction of sodium chloride by saying that first of all, by just writing on a paper, first of all that sodium in the solid phase first of all undergoes sublimation. So there is a enthalpy change accompanying the sublimation of sodium in solid phase to sodium in gaseous phase. Now when sodium converts to in the gaseous phase, that is gaseous sodium atoms, then gets ionized to give sodium ions in the gaseous phase. This represents the ionization energy, the energy required to ionize the atoms in the gaseous state to the respective ions in the gaseous state. Then there is atomization enthalpy, or the bond dissociation enthalpy we can also say here for chlorine, because half mole of chlorine is been used in this balanced chemical equation. So there is half of bond dissociation enthalpy, bond dissociation energy for this dissociation of chlorine molecule to chlorine atoms, so which are in gaseous state. Then when we ionize them by giving one electron to chlorine atoms in the gaseous state, the result we get is the chlorine ions in gaseous state, and the energy which is obtained in this process is known as electron affinity. So we need to take the sum of the enthalpy change for sublimation of sodium metal, then we need to add to this is the ionization enthalpy, then we need to add is the half of bond dissociation enthalpy for the atomization of chlorine from gaseous chlorine to the chlorine atoms in gaseous phase, and then we need to add to this is the electron affinity for ionization of chlorine atoms to chloride ions, and combination of the sodium ion and chloride ion in the gaseous phase, which when do combine to give sodium chlorides in the solid phase. Whenever these ions in the gaseous phase combines to give a condensed solid, there is an energy corresponding to an amount, there is a heat corresponding to an amount that is called lattice energy is released by the system. So therefore, either we take the sum of all these steps and we write the enthalpy of formation, or we write the enthalpy of formation as such. This has been the same. So it does mean enthalpy of formation for sodium chloride is basically a sum of sublimation enthalpy of sodium metal plus the ionization enthalpy of sodium metal to sodium ion conversion, and then half the bond dissociation enthalpy of for chlorine molecule. Added to this is the electron affinity for chlorine and plus the lattice energy. The combination of all these basically equals to the enthalpy of formation of sodium chloride. Suppose we have the data set on enthalpy of formation of sodium chloride, which is known to us. Enthalpy of sublimation of sodium is also known. Ionization enthalpy, bond dissociation enthalpy, electron affinity, all these are known. Then what remains unknown in this linear equation is the lattice energy. So which we can rearrange this equation and we can determine the lattice energy from this manipulation of this equation. This is how Hess law also helps in calculation of lattice energy of various salts, ionic salts. Basically, now the question arises, what for this exercise we have done, that is what is the purpose of calculation of lattice energy. Basically, the lattice energy is an important criteria based upon which we can talk about the stability of a given ionic solid. Greater is the lattice energy, greater is the stability of an ionic solid. And from the stability of a solid, ionic solid, we can discuss very many physical properties for ionic substances, ionic solids. Having said this, now we switch on our attention now to the bond enthalpy. What is basically the bond enthalpy? Well, before we talk about anything in this manner, for example, whenever a bond is formed, the energy, corresponding energy is released in the surrounding, whereas whenever a bond is broken, whenever we want to break a bond, we need to put in energy to overcome the attractive forces, and the energy which is being put in, that is used to break the bonds, to separate the radicals or atoms apart. So, therefore, bond breaking is an endothermic process, that we must keep in mind. So, therefore, bond enthalpy now we should talk about. The bond enthalpy is the average of enthalpies required to dissociate a said bond present in different gaseous compounds into free atoms or radicals in the gaseous state. And basically, why bond enthalpy data is important is that we can use to calculate approximate values of enthalpy change for a given reaction. How we can do that? We will see it little very shortly from now. For example, we have seen this, whenever bond breaking occurs, we need to pump energy into the chemical system to break the bond and to separate the atoms or radicals apart. In the making of bond, the exactly opposite thing is true. That is, if we want to make new bonds, energy is released when new chemical bonds are formed. So, it means breaking or making same chemical bond will require the same energy to be put in or released. That is, when suppose we need to break a hydrogen molecule, the energy corresponding to the dissociation energy of hydrogen needs to be given to the system, that is here equal to enthalpy change for the dissociation of hydrogen. It requires 432 kilojoule of energy per mole of hydrogen molecules, which when undergo decomposition. Same way, in the same manner, when 2 moles of hydrogen atoms do combine to form 1 mole of hydrogen, in this reaction also, because this reaction is the reverse of the first reaction, so therefore enthalpy change should be the same in magnitude as the first reaction, but with opposite sign, because this reaction is reverse of the first reaction. So, therefore, it becomes important to understand that in an bond breaking is an endothermic process and bond making is an exothermic process. So, now question arises, what way we can make use of data on bond enthalpy to get to the value of enthalpy of reaction. Let us have a consideration of this chart, with the help of which we can understand this whole process. You see, whenever reactant molecules we have, whenever they to transform to the products, suppose for example, the left hand side we can see here this represent an endothermic reaction, because if we consider the enthalpy consideration, the sum of reactant molecules have their enthalpy which is lower as compared to the product molecules. So, therefore, this reaction occurs with the absorption of heat, and the products have greater enthalpy corresponding in comparison to those of reactants. So, we can say that there is one path the reactant can directly transform to product, but we can theoretically consider another path. That path is that the reactants do undergo dissociation leading into the formation of gaseous atoms, and then these gaseous atoms do combine in different manner and do form different chemical structures which are known as products. Same way, we can rationalize the same thing in the exothermic process also. For example, reactant molecules which are lying at higher enthalpy, the sum of enthalpies of reactants if that is higher as compared to sum of enthalpies of products which are lower. So, then when a reaction occurs in such reaction, there occurs a decrease in enthalpy of the reaction system from higher enthalpy to the lower enthalpy side whenever reaction occurs as a result of transformation of reactant to products. So, basically we can view this as one path, we can view also this as another path. First is the breaking all the bonds in the reactant molecules leading to which leads to the formation of atoms. That we can do by taking sum of bond enthalpies of all the bonds in the reactant molecule, and then we have atoms, separated atoms, which would combine in different manner in the chemical structure of the product so as to give a number of bonds in the product chemical species, for which we can add the bond enthalpies of all the bonds which occurs in the products. So, basically we can say that it is the difference of sum of bond enthalpies of reactants and products that would actually lead to the enthalpy change for the reaction. So, this is another way, utilizing the data on bond enthalpies we can get the enthalpy change for a desired reaction. So, we need to, I would say that we can only determine the approximate values of enthalpy change for a desired reaction. Why approximate? We need to understand it from the viewpoint of the definition, from the definition of the bond enthalpy itself. Basically, let us consider we have methane gas, methane in the gaseous state under standard conditions. So, whenever we give heat to methane, by absorption of heat, there could be a possibility that there occurs first dissociation. There are 4 equivalent CH bonds in methane. So, therefore, what we can do is, when we supply heat, there may occur the dissociation of first CH bond. It will lead to the formation of the CH3 free radical as well as a hydrogen atom. Then if we further supply heat, then in a stepwise manner the heat which will be required to let the dissociation of the second CH bond from this methyl radical will be more than that of the heat which was required, or energy which was required to dissociate the first CH bond in the methane. But all these CH bonds initial in the methane molecule were all equivalent, but they require different thermal energy to dissociate all these CH bonds. So, what we can do is we can take the mean of all these 4 dissociation steps, enthalpy change for all these 4 dissociation steps, and we can take the mean of them, of all these. What we will formulate it as the bond enthalpy of the CH bond, and we can make use of this data set, that is the bond enthalpy for CH bond, for the calculation of enthalpy change for other reactions. We will see very shortly how come. But the fact of matter is, in methane molecule all CH bonds are equivalent, and we could make use of CH bond data, this CH bond data, to calculate exactly the enthalpy of formation of CH4, that is methane. But if we make use of this dissociation enthalpy of CH bond to calculate the for example, to calculate the enthalpy of formation of some other organic compounds, then this may not be very accurate. Why? Because there is a particular environment of these CH bonds in methane, which may be different from the environment, the chemical, the electronic environment within a molecular species in some other molecule. But which data set we will be making use of? We will be making use of this same data set on the bond dissociation, bond enthalpy of the CH bonds in the methane molecule. So, as a result, if we make use of these bond enthalpy data in the calculation of enthalpy change for some other reactions, then the enthalpy change for those reactions, for those desirable reactions for which enthalpy change we cannot determine experimentally, those enthalpy changes would be approximate value, because we have used the data of bond enthalpy for CH bonds in which were present in a different environment as compared different electronic environment which were present in the which would be present in the given or desired compounds. We would see it with the help of an example. Let us take an example. What is the, now question arises in this example that what is the enthalpy change when hydrogen is added to ethane or acetylene to say to produce ethane. So, our desired reaction is that C2H2, the acetylene which to combine with hydrogen, both these in the gaseous species, both these are gaseous species to form ethane molecule in the gaseous state. What would be the enthalpy change for this reaction? To answer this, we must look at what types of bonds which needs to be broken in the reactants and which needs to be formed in the products. Let us have a look at it. In this reaction, we first we need to break all the bonds inside the reactant molecule. So, it means in C2H2 acetylene there is one carbon-carbon triple bond and two carbon-hydrogen single bonds, right. And in addition, we also have in this reaction, we need to form, in addition we also need to form the bonds in two hydrogen molecules also. You see, first of all, let us once again take a look at it. In this reaction, we have C2H2 acetylene, this is this molecule as one of the reactant, and two hydrogen molecules also serve as reactants. So, if we consider this reaction in a way that first of all we need to break all the bonds in the reactant molecules to give to the gaseous atoms, then all we need to do is we need to break one carbon-carbon triple bond is this bond, and then we need to break two carbon-hydrogen single bonds, and in addition we also need to break two hydrogen-hydrogen single bonds. So, this will lead to this will give us the carbon atoms and hydrogen atoms, the necessary carbon and hydrogen atoms which are required for the formation of ethane. Here in this ethane, we have instead of one carbon-carbon triple bond, we have one carbon-carbon single bond, and moreover, rather than just one carbon-hydrogen single, two carbon-hydrogen single bond, this molecule has 6 carbon-hydrogen single bond. So, this we have identified now which bonds needs to be broken and which bonds needs to be formed. So, first of all, that is the full structure we need to draw, just we have drawn, and this will exactly show what bonds are involved, and this is exactly what we had written. After this, we need to make a list of all the bonds being broken. As I have told you, there is just one carbon-carbon triple bond needs to be broken, and two carbon-hydrogen single bonds and two hydrogen-hydrogen single bond needs to be broken. Then, so therefore, these are the bonds which we need to break. That is one carbon-carbon triple bond, two carbon-hydrogen single bond and two hydrogen-hydrogen single bond. And thereafter, after this bond breaking, we need to go to step 3, that is we need to fill the values of the bond enthalpies, which we will do it little later. That is the enthalpy change for this reaction, that is for the breaking of one carbon-carbon triple bond is 835, all these values are in kilojoule per mole values. So, here it is 2 into 414 because bond enthalpy for CH bond we have considered it to be 414 from consideration of bond enthalpy from dissociation of methane, 4 bonds in methane, and here breaking of one hydrogen-hydrogen single bond requires 432 kilojoule per mole of energy. So, we also need to multiply it by 2, and so therefore, we get all the total enthalpies as 835, 828, 864. We need to take the sum of all these. This will represent the total amount of energy which we need to supply to the reaction system to break all the bonds in acetylene and molecular dihydrogen. So, now we need to repeat this whole process for bond making step also. Let us see, in this bond making we have one carbon-carbon single bond which needs to be formed, and in addition we require 6 carbon hydrogen single bonds which also needs to be formed. Whenever a bond is formed, heat is produced, and whenever a bond is broken, heat is absorbed. So, it does mean that bond breaking is an endothermic process and bond making is an exothermic process, but we have just not written the sign over here. Now, here it is the signs which we have introduced. Here the bond making, in the bond making energy is released. So, we need to give a negative sign to the bond making process of all the bonds. One single carbon single bond needs to be formed. So, there is an enthalpy change accompanying this bond making. We need to add to the 6 times enthalpy which is involved in the bond making process of 6 carbon hydrogen bonds, single bonds. So, therefore, this is negative 2484 kilojoule is the negative 2484 is the kilojoule is the heat which would be involved in the process of making of 6 carbon hydrogen bond, and in the making of one carbon-carbon single bond there is minus 346 kilojoule of heat will be involved, with the sum total of this would be. So, that is when from the gaseous atoms, when the ethane molecule gets produced, there occurs a heat evolution, that is minus 2830 kilojoule per mole, and whenever such all the bonds in the reactants are broken, 2527 kilojoule per mole of energy needs to be given to the reaction system. So, if we need to calculate the enthalpy change for the reaction, we need to take the sum of these processes, the enthalpy, sum of the enthalpies involved in the process of bond breaking and bond making, and when we do so, what we get is that sum of the heat required to break all the bonds in reactants plus the sum of heat which gets evolved in the process of bond making. So, ultimately it amounts to minus 303 kilojoule per mole. So, this is an approximate way of calculation of enthalpy change for a given reaction by virtue of using the data on the bond enthalpies of all the bonds which needs to be broken and all the bonds which needs to be formed. So, this way also we can determine the enthalpy change for a reaction. Having said this, let us sum up now once again. The enthalpy change for a reaction is formulated as the sum of molar enthalpies of products less the sum of molar enthalpies of reactants, each multiplied with their stoichiometric coefficients. Since we cannot determine absolute values of molar enthalpies, therefore, we cannot determine enthalpy change for a reaction using absolute enthalpy data on the substances. Then we make use of, and first of all we conceptualize the concept of enthalpy of formation, and then we relate the molar enthalpy of substances with the enthalpy of formation, that is of compounds. Making use of molar data set on molar enthalpy of formation of compounds, that also helps us to determine the enthalpy change for the desired reactions. But enthalpy of formation we cannot determine for very many formation reactions. This is a practical inability. In order to address this, we appeal to the combustion reaction. We first of all conceptualize the combustion reaction. We use the enthalpies of combustion reaction for the calculation of enthalpies of formation reactions, formation of certain compounds, and which we can make use of further in the calculation of enthalpy of reaction. But combustion reactions are also does not even occur in definite proportion except for the combustion of of organic compounds which are composed of only carbon, hydrogen and oxygen. So, therefore, we need to look for further options available, and one such option is the bond enthalpy data. We can make use of bond enthalpy data first of all in order to calculate the enthalpy change for a given reaction. So, first of all we write a given or desired reaction. We first of all try to write all the reactants and all the products, and we try to identify how many bonds and which kind of bonds are there present in the reaction system, and from that observation and we further observe how many bonds and which types of bonds needs to be formed in the product side also, and then we take the sum of bond enthalpy of all the bonds which needs to be broken. So, since bond enthalpy is a positive value because the dissociation of a compound is always an endothermic process, then we can add to this is the enthalpy involved in the making of all the bonds which occur in the product side, just by taking the negative with a negative value of the bond enthalpy data of all the bonds which are present in the product molecule, and taking a sum of all these. In this manner, the sum of all these bond enthalpy data, we get the final value of enthalpy change for a desired chemical reaction. This is the way we can determine the enthalpy change of a reaction. So, 4 ways basically: conceptualized with the help of molar enthalpy of substances, first calculated with the help of molar enthalpy data, molar enthalpy of formation, standard molar enthalpy of formation data, then using standard molar enthalpy of combustion data. If these two fail, then we can make use of Hess law, and we can further even certain reactions, if we do not find some certain sequence of reactions which lead to the ultimate overall desired reaction, then we can appeal to the bond enthalpy data, and using which we can calculate the enthalpy of reaction. And basically this bond enthalpy data is very useful in calculation of enthalpy change for those reactions which are quite unknown, so and are practically difficult to handle. And it may be mentioned here that the enthalpy of reaction using the bond enthalpy data is only an approximate value, because whatever the bond enthalpy data for the various bonds which we had used, those were the data set which were obtained for dissociation of various kinds of bonds in different environment, and the product which we are seeking here in the desired chemical reaction, in that product those bonds may be present in a different electronic environment. So, on this basis we can say that the calculation of enthalpy of reaction using the bond enthalpy data is only an approximate way of calculation, and the enthalpy of reaction using this bond enthalpy data is only an approximate value. So, with this we come to the end of this lecture. In the next lecture we would try to see the dissolution process and certain other physical processes in which enthalpy change in the chemical reaction systems occurs. So, on this note I would say thank you very much for patiently listening and learning. Thank you.
Thank you so much, sir, and that was an extremely interesting lecture. And of course, now that we have traced a series of these 3 lectures, they would be able to clear the concept and idea even better, and it can be viewed on YouTube for the students. And sir, since we are progressing quite at a pace of as part of chemical thermodynamics, would you suggest to us, are we going to take it further, or we are going to introduce a newer idea after this?
Oh well, yes, as the chemical thermodynamics is a very vast topic in itself, since we have conceptualized all the basic concepts in chemical thermodynamics, following which this is the first application of chemical thermodynamics is the thermochemistry, where this helps us to determination of enthalpy changes for various chemical reactions, but this is no guarantee for on what basis we can say the chemical reactions occur. So, there are lot many physical quantities which needs to be defined, and on these lines we will conceptualize very many bookkeeping properties in thermodynamics, and following which we will progress further.
Right. Thank you so much, sir, for an in-depth explanation on that also, so our students will get a bit of idea of what they must be looking forward to. So again, thank you so much, sir, for being here today, and thank you viewers for watching us. Have a wonderful day ahead.